You ever wonder why a little pebble feels way heavier than, say, a big piece of styrofoam? Or how a massive steel ship can just float on the ocean? Well, it all comes down to one simple but super important idea: density. So let's get into it and figure out exactly why some things are so heavy for their size.
All right, to kick things off, let's do a little thought experiment. You've got two balloons, exactly the same. One's filled with water, the other's filled with air. Now, you already know which one is heavier, right? I mean, it's the water balloon, obviously. But why? They're taking up the exact same amount of space.
And that's where this magic word comes in: density. At its simplest, it's just a way of talking about how much stuff, or mass to be scientific, is crammed into a certain amount of space, or volume. That water balloon has a whole lot more stuff packed inside of it compared to the air balloon. And that's density in a nutshell.
Okay, so to really get what density is all about, we've got to shrink down. I'm talking way, way down. We need to look at the tiny little particles that make up everything. Because the way those particles are arranged, well, that's the whole secret to why solids, liquids, and gases are so different from each other.
First up, let's talk about solids. Just picture the particles inside a solid, like a block of iron. They're jammed in there, shoulder to shoulder, in this tight, orderly grid. They can't really go anywhere, they just kind of vibrate in place. And because you have so many particles packed into a small area, solids tend to have a really high density. Now, with liquids, things get a little looser. Think of it like a crowded dance floor. The particles are still really close, but they're not locked down. They can slip and slide past each other, which is why liquids can flow. This slightly more relaxed arrangement means liquids are usually a bit less dense than solids. And then we get to gases. Oh man, this is a whole different ballgame. The particles in a gas are just zipping all over the place. They're super far apart from each other, with tons and tons of empty space in between. So naturally, since there's hardly any stuff in the same amount of space, gases have a very, very low density. So this chart just sums it all up perfectly. For solids, you've got tightly packed particles, which means high density. For liquids, they're close, so you got medium density. And for gases, they're far apart, giving you a low density. See the pattern? It's a super simple relationship. The closer the particles, the denser the material.
Let's put some actual numbers on this, because the difference is kind of mind-blowing. Check out the density of steel. It's almost 8 grams for every little cubic centimeter. Then you have water, which we use as a baseline, right? They're at 1. But then look at air. It's barely over 1,000th of a gram. The difference isn't just big, it's gigantic. Okay, so the concept makes sense, right? But how do we actually, calculate this stuff? How do scientists get those numbers? Well, that's what we're diving into next. And don't worry, it's actually way simpler than it sounds. It all boils down to one little formula.
And there it is, the big secret. Density is just its mass divided by its volume. That's it. You just take how much stuff is in the object, that's the mass, and divide it by how much space the object takes up, that's the volume. And boom, you've got its density. So let's put this formula to the test. Imagine we have two cubes, and they're the exact same size. They both have a volume of 8 cubic centimeters. One is made of iron, and it has a mass of 63 grams. The other is wood, with a mass of only 4 grams. Same size, totally different amount of stuff packed inside. So let's run the numbers for that iron cube. It's super straightforward. First, we know our mass is 63 grams and our volume is 8 cubic centimeters. Then we just grab our formula. Density equals mass divided by volume. We plug in the numbers, 63 divided by 8, and what do we get? The density of iron is 7.9 grams per cubic centimeter. See? Easy. Okay, so we've got this nice, neat rule, right? Solids are almost always denser than liquids. But, science always has that one weird exception to the rule, and this is one you see literally every day. And that brings us to a really cool puzzle. If solids are supposed to be denser, why on earth does ice float? Why does an ice cube in your drink bob right to the top instead of sinking? I mean, an iceberg is just solid water, so what's the deal? Well, here's the secret. Water is just weird. It's a total rebel. Unlike almost anything else, when water freezes, its particles don't huddle closer together. They actually form this special crystal structure that takes up more room. So the particles actually move a bit farther apart, which means solid ice is, get this, less dense than liquid water. And that's exactly why it floats. So this whole density thing isn't just for science class. It's everywhere. And it has huge effects on everything from the things we build every day all the way out to the most insane objects in the entire universe.
Think about this. Ever seen those little gaps in railway tracks and wondered what they're for? Well, on a hot day, the steel track heats up, and its particles start vibrating and pushing each other apart. The track actually gets bigger, its volume increases, but the amount of steel, the mass, stays the same. So what does that mean? Its density actually goes down, and engineers have to leave those gaps so the tracks have room to expand without buckling. Okay, we've talked about trains. Now let's go to the absolute extreme end of the scale. Picture an object in space, and it's tiny, cosmically speaking. It's only about 20 kilometers or maybe 12 miles across. That's about the size of a city. But what if I told you that this little city-sized ball has more stuff in it, more mass, than our entire sun? All that matter crushed down into a space that is impossibly small. It's called a neutron star, and its density is something that's really hard to even wrap your head around. To try and put that in perspective, if you could somehow get a teaspoon of the stuff, that one little spoonful would have a mass of around 5 billion tons. That is the same weight as about 900 Great Pyramids of Giza, all crammed into a single teaspoon. That's the mind-bending power of extreme density. So, we've seen how a single idea, density, explains floating icebergs, expanding railways, and even the craziest stars in the universe. It really makes you think, doesn't it? If one principle can explain all of that, what other fundamental rules are out there, just hiding in plain sight, waiting for us to figure them out?